In yesterday's tutorial, we successfully created a simulation using simulation nodes. However, in today's tutorial, we're going to step it up by just one notch to create another simulation, except here we're going to keep the particles within a sphere to create an effect that I've always wanted to create. And previously, you'd require a lot of particle simulations, which would be really hard for your laptop or your computer to actually handle if you have a low-end PC. But with the new simulation nodes, you can create it fairly easily. So let's figure out how we can do it. In our default scene, we're going to bring our cursor to the junction of these two windows, click and drag to create a new window, and then change the window type from the 3D viewport to the geometry node editor. Then we'll press this plus button to create a new geometry node tree, and we'll start it off very similar to exactly what we did last time. So everything till the self collisions is pretty much going to be the exact same. However, since simulation nodes is a fairly new concept, it's always good practice to go through the entire thing once again instead of blindly copy pasting from previous Blender files. So let's select the group input, press X to delete it, and the first step was distributing a bunch of points within a cube. So I'll press Shift A and search for a cube node and then plug the mesh into the geometry. I'll increase the size to something like 5 meters and just drag this to the side. Now I need to convert this to a volume so that we can distribute points within that volume. So I'll press Shift A and search for a mesh to volume node and change the voxel amount down to 2 and just increase the exterior bandwidth a little bit so that we have some breathing space. Then I'll press Shift A and search for a distribute points in volume node and plug that in right after the mesh to volume. Now I'm going to increase this density before actually caching or baking the simulation, but till then I'm going to keep the density down at some low value like this. After that, we have to actually set the radius of the points. So I'll press Shift A and search for a set point radius node, plug that in and change the radius to maybe 0.1 meters. Now we need to delete all the points that are going to be outside the bounding sphere, which I'm going to keep as about 5 meters. And also I don't want to hard code the value of the point radius because we might use that for calculations later on. So I'll press Shift A and search for a value node and I'll just place it here. I'll select it and go to the node tab over here and change the label from value to point radius and then place the value at 0.1 over here and plug this value into the radius of the set point radius. Then I'll duplicate this point radius node by pressing Shift D and then labeling this one as the bounding radius and then change that to about 5 meters. So I'll just give it a value of 5. Next, I have to actually find the position of every single one of these points and compare it with this particular 5 meters. And if it's beyond that 5 meters, it has to get deleted. So I'll press Shift D and search for a position node, which gives me the position of every single one of these points. Then I have to find the length of the position vector. So I search for a vector math node and change it from add to length, because remember, if I find some particular point over here, what this position is going to return is a vector that goes from the origin to that particular point. Now, if I find the length, I'll just get a single number which is equal to the length of this vector. So I'll go ahead and plug this position in here. And I want to check if the length is greater than this bounding radius. So I'll press Shift A and search for a compare node, and I'm going to keep it at greater than itself. So is this vector greater than the bounding radius? So plug the bounding radius in, and if it is, then the point should get deleted. So I'll search for a delete geometry node, plug that in, and use this result as the selection. Now we should get a spherical point cloud, which is exactly what we want. Next up, we're actually going to start the simulation. So I'll press Shift A and search for a simulation zone, and then just connect the geometry into the input geometry and plug the output geometry into the geometry of the group output. Now we're going to separate out the simulation into a few distinct simulations. So the first one is going to be self collisions, as we did last time. The second one that we're going to be doing this time is going to actually be simulating gravity, because we want the particles to actually fall down as well, unlike last time. The third thing that we need to simulate is the bounding box. And beyond this, for both this self collision as well as the bounding box, we're going to use subframes as well, which means we're going to have multiple simulations within every single frame. So between frame 1 and 2, we're actually going to simulate the self collisions and the bounding box and update it multiple times. So it's going to be a fairly long one, but I'll have all of the timestamps given in the description so that you can skip to whichever section you find the most relevant for you. So the first thing that we have to do is the self collisions. To find out if a particle is colliding with another particle, we can find its position and the position of its nearest neighbor and check whether it's lesser than twice the radius of each point. And if it is, then it is colliding and they have to move. So to make something move, we press Shift A and search for a set position node, and we can just plug that in after the simulation input. Next, we have to actually figure out how much they have to move by, and we have to find out which of the particles have to move. So we'll start off with which of the particles have to move. For that, we need the position of each particle. So we search for a position node, and we need to know which one is the nearest particle to it. So I press Shift A and search for an index of nearest node, that we get the index of whatever is nearest to this particular position. So I plug the position into the position, and we need to actually evaluate the position position of whatever is there at the nearest index. So I search for an evaluate at index node and plug the index into the index, and for the value I need it to be the position, which is a vector, so I change it from float to vector and then plug the position into the value. Now this particular value has to go into the compare node. So now we have the position of the particle and the position of the nearest particle. To find out the distance between them, we can press Shift A and search for a vector math node, and we can change it to distance. However, we also get a vector that has length equal to the distance if we just subtract them. So instead of finding the distance this time, we're directly going to use the subtract node, and we're going to subtract the position of the particle from the position of the nearest neighbor. Now the reason why this order is important was explained in the previous video, so I highly suggest checking out that previous video if you haven't. It will be linked in the description as well as in the top right corner at the moment. Now we have to compare the length of this vector to twice the radius. So to find the length of this vector, I'll press Shift A and search for another vector math node and change it from add to length, and now we have the length, or essentially the distance between these 2 points, and we have to actually compare it with twice the radius. So we have the point radius over here, so we can search for a compare node, plug this length into the top value and plug this point radius into the second value, but we need twice the point radius, so I have to search for a math node, plug that in before the greater than node, and then change this from add to multiply and multiply it by 2. Apart from that, if I want some tolerance, which means I don't want them to perfectly have to actually touch to create repulsion, I can just duplicate the math node, change it from multiply to add, and then just add in some tolerance value. So maybe because the radius is 0.1, I'll add in a tolerance of 0.05, and that is good enough for this particular section. Now this result is what's going to act as the selection of our set position. So I'm going to plug this into the selection, and I have to now figure out by how much it should move, and it should move essentially by the subtracted amount scaled down by some value. Because if we directly use this subtracted value, remember this subtracted value is a vector. So let's assume we have the 2 points intersecting with each other as point A and point B. The output of this subtract value for point A is going to be a vector pointing in this direction like this, and for point B, when it is evaluating it for point B, it'll be a vector pointing like this. So essentially we need this to actually move in this direction. So we need point A to move in this direction, and we need point B to move in this direction. So the direction is proper, but this length, we don't need it to move by this entire length. We need it to move by a smaller length itself, which would be enough to get it beyond the surface. So imagine these are the 2 points. This is our vector. If we directly subtract this vector, the new point is going to move by this distance. So that's approximately here, and have a circle like this, whereas this point would move by this amount on this, and this would be the new position after the first frame itself. So that's a huge motion that's present, and the velocity becomes really, really high between these two. However, if we scale it down by a smaller amount, we can get the new positions to simply be here and here, which seems like a much better simulation. So I'll press Shift A and search for a scale node, which does not exist. It's still a vector math node, and I have to change the type from add to scale, which just reduces the value on all of the axes by a single value. So now I'll scale it down by something like 0.2 and then plug this vector into the offset. So now if I play the animation, we get these points continuously moving, and that is again because we have this as greater than, but it should be less than, because if the distance between them is less than twice the radius, then they have to move. I think I made the same mistake in the last video as well. Sorry for that. We're going to change this from greater than to less than. Now we have to go back to frame 0 and play the animation, and everything should move apart till they don't touch anymore. Now of course, because our density is so low, it seems like nothing is moving. So just to test out our setup, I'm going to increase the density to something like 50, and then I'm just going to play the animation, and yeah, we do see that everything is moving, and they should keep moving until they reach a situation where they are not intersecting with any other particle. So that seems all right. We can reduce the density back to maybe 10 and start off with the next portion of the animation, which is the second simulation, which is the actual velocity. For the velocity, we have to find out the initial position of every single one of the particles, and after the simulation what the final position is, and if we subtract those two, we get the velocity per frame, or the distance moved per frame. So we have to capture the initial position. For that, we search for a capture attribute node, plug that in over here, and we change this from float to vector because the position is a vector. Then search for a position node, plug it into the value, and this attribute is essentially the initial position. Now we need to find the final position, so we can press Shift A and search for a position node here, and we have to compare these two positions, or we have to subtract them. So we search for a vector math node, change it from add to subtract, and we want the final position minus the initial position. The final position is here. We plug that into the first socket. The initial position is this particular attribute. So we plug that into the second socket. And then this output, we can plug directly into the simulation output and call that velocity. So right now it's called vector. To change the name, we select the simulation output node, and then under the simulation state, you can see we have a vector. We can change that to velocity, and that is going to also be reflected in the simulation input. Now, for the simulation input, we need this particular velocity to change the position of the particles accordingly. So I search for Shift A and search for a set position node and plug that in. And for the offset, we use this particular velocity. Now, if you actually play the simulation, if a particle starts moving, it should continue moving forever, which is exactly what's happening. And they're all dashing into each other, which causes all of them to eventually move. So now we need to actually dampen out the velocity because there should be some sort of friction that stops it over time. To damp it out, we search for a vector math node and we just scale it down. So we plug that into this offset and change it from add to scale and scale it down to maybe 0.95. So now if I play the animation, they start moving, but eventually every single particle will also damp out and stop, which is exactly what we want. Now that we have the velocity set up, we need to actually create the gravitational attraction. So essentially gravitation is an acceleration. It's a form of acceleration, which is a change in velocity, which means every single frame, the velocity has to increase by a certain amount. So essentially we know the gravitational acceleration is 9.8 meter per second square. This means every second, the velocity increases by 9.8 meters. Now, if we're animating at 30 frames per second, I'll go ahead and change that right now. Change the frame rate to 30 frames per second. This means for every frame, please ignore my handwriting. I can't do anything better at the moment, but yeah, for every frame the velocity should increase by 9.8 divided by 30 meters per second, or in this case meters per frame, because we're going to be evaluating the speed for every frame. So if we quickly pull up a calculator, we can see 9.8 divided by 30 is approximately 0.32. So for simplicity, I'm actually going to use 0.3 itself, and essentially the velocity has to increase by 0.3 every single frame. So how we're going to do that is by simply adding to this velocity just before it passes out as the simulation output. So I press Shift A and search for another vector math node, and I have to add in this velocity that we just calculated. So it increases by how much every single frame? What we calculated was it increases by minus 0.3 every single frame. So why we're using minus is because gravity is generally in the downward direction, so it has to move down, and it's only in the Z axis. So now if we actually go back to frame 0 and play the animation, we should get something that falls down, which is perfectly simulating gravity. So it keeps accelerating and going faster and faster as it goes down. So that seems great. However, as usual, I don't want to actually hard code this value because there might be a situation where this is not a realistic simulation and you want it to be really slow. So you might want this value to be 0.1, or maybe you don't want gravity to act in the downward direction. You want it to act in some arbitrary direction. So for that reason, I'm actually going to come all the way back here where we have our values, and I will press Shift A and search for a vector because again, gravity is a vector, and I'm just going to change this over here to maybe minus 0.3 and then plug this value into the add node over here. So now we've simulated self collisions with velocity as well as gravity. The next thing that we have to actually do is simulate the collisions within the bounding sphere. To do that, the first thing that we have to do is actually create the bounding sphere. So I'll press Shift A in the 3D viewport and then search for an icosphere. Now I'm going to expand the icosphere settings over here and increase the subdivisions to something like 5 that we get it fairly smooth. Maybe even 6 will do. And then I'll collapse it and I will just scale it by 5 units. And this is going to be our bounding box. So I'll change this name over here from icosphere to bounding box. And then I have to drop this into my geometry nodes. So I'll select the geometry node object again and take this bounding box and bring it in. Now this is again going to be fairly similar to what we did last time for the collision with an external sphere, except this time the particles have to be present within the sphere. So I have to find the position of every particle and the position of this particular sphere and then compare them to figure out whether these particles are present outside the sphere or inside the sphere. If they're outside the sphere, I need them to get pushed back in. So I'll press Shift A and search for a position node, and now I have the position of every particle and the position of the sphere, but the sphere is going to be animated and it's going to move around, so I'm going to change it from original to relative. Next, I'll press Shift A and search for a vector math node, node, and I want to actually subtract the two positions, and then I'll plug in position into the first vector and the location into the second vector. So now I essentially should have a vector pointing from whatever the location of my sphere is to every single point in my point cloud. Now, if this vector is greater than the radius of this external sphere, that means the point is outside the sphere. So I have to first find the length of this subtracted value. I press Shift A and search for a vector math node, change it from add to length, and then plug this value in. And I have to compare whether this length is greater than the radius of this sphere. Now remember that we found out in the previous video itself that the radius of an icosphere is equivalent to the scale as long as you don't apply it. So make sure that you don't apply the scale. That means do not press Ctrl A and apply scale, and just leave it as is. And that way this scale value over here is equal to the radius. So I have to compare them. So I press Shift A and search for a compare node. And yes, if the length is greater than the scale, then they have to move. But again, this greater than might want some tolerance because you don't want these particles to actually completely come and touch the outside edge. So I'll search for a tolerance, which is going to be just a simple math node set to subtract, because if this is the radius, I want to just subtract a tiny amount. So maybe go to this much. And if a sphere reaches this particular position, it should start moving back in and not go till the absolute edge. So that's why we're just going to subtract the tolerance value. It'll also make it seem like the glass object is actually thick. So I'll subtract maybe a value of just 0.2, and that should be all right. If it's greater than, we need it to get pushed back in. So all motion is done with set position nodes. So I'll press Shift and search for a set position node, plug that in over here, and then this result is going to be the selection. Now, how much is it going to move? We have to yet determine. Now, if it's present outside the sphere and we want it to come into the sphere, it should obviously move towards the direction of the sphere. But right now we have position minus the location, which means we have the position of the points minus position of the sphere. That means that the vector that we have from this subtract node is pointing towards the points. So we have our sphere here, we have our point here. This vector is pointing like this. However, we need this particle to move in the opposite direction. So there's multiple ways in which you could do that, and possibly the easiest way would have simply been to connect this position in the bottom socket and this location in the top socket. But since we know vector math, I'm going to use a vector math node and change this from add to multiply or scale, and I'm going to scale it by -1, and that simply reverses the direction of the vector. Now, yes, this is including an extra node that's unnecessary, but I think you will come across situations where you need to reverse the direction of the arrow in many other simulations that you do. So if you know this trick, it will be helpful when you're planning out your next animation. Now, again, we don't want particle to get pushed in super fast by using this vector. We want it to actually be much slower, so slowly get pushed in. Hence, we're going to use another scale node. Press Shift D and duplicate it, and this time scale it down by just a small value. So I'll change it to maybe a value of 0.2 and then plug this vector into the offset. So now to actually see the spheres, you can switch on X-ray by pressing this particular button, and now we can see all of the points present inside. And if you actually play the animation, we see due to gravity everything's falling down, and due to the collision constraint it's staying at the bottom, but particles are clearly able to get too close to each other. So I want to actually increase the tolerance of the self collisions. So this add value was the tolerance, so I'm going to go ahead and just increase this and then replay the animation, and now they're not able to get into that close of a proximity. But no matter what we do, they're still gonna keep coming fairly close to each other, because even after we push them out, they do get pulled back down due to gravity that's added right at the end. So that's why even if they get pushed out by this set position node over here, due to gravity they get pulled back and they continue inward. And that is actually why we need substeps, which implies we need to redo this calculation multiple times within a single frame to make sure that they never get this close to each other. So the way we can do that is by actually just repeating this entire thing again. And to make it easier, we can set all of these nodes into one single node group. So we select all the nodes necessary and then press Ctrl G to create a node group. Now there is one input that's coming from beyond, which is the radius of the spheres. So I want this to also be present as an output, that we can just connect it into the adjacent node. So I plug that into the output, and we can press this button over here to go back to the original geometry node tree. And right now, again, the node group is just labeled as node group, so we can change this as self collision substep. And now we can just duplicate this multiple times. So press Shift D, bring it here, and plug the value into the value. Now again, Shift D, and maybe have 5 stop steps for each frame. So I'm gonna have to duplicate this 5 times. Along with that, I also want this point radius to be a little larger. So I'm gonna keep it at 0.5, and I'm actually gonna keep it at 0.1 so that we can actually test our subframes or our sub steps and check if that's that's working fine. Later on, I'll increase the radius. Now I just play it, and now you see they can't get as close to each other as they were previously, and that's because of these substeps that's being calculated. Apart from that, I now want to increase the actual point radius, so I'm going to increase this to 0.5, and then I'm going to play the animation again. That seems alright, but I want to actually decrease it to 0.2. Now that I have all of these particles being simulated over here, I need to actually play around with the fact that they actually end up going through the sphere at the beginning, and if you were to move the sphere, they're also going to move around. So let's select the sphere and actually start the animation and move the sphere around. You can see that the particles do follow the sphere, but clearly they're actually exiting the sphere as well before they get pulled back in. So to fix that, we need some substeps towards that bounding box collision as well. So go back to frame 0, select our geometry node object and create a substep for this entire section, which is our bounding box. So select all the nodes necessary, press Ctrl G, and this is our subgroup. Press this button to go back on top and label this group as bounding box subgroup or substep. Then again, we want to do this 5 times per every frame, so Shift D and do that 5 times. Now note that the more substeps you add, the more precise your animation will become. However, it's also going to take much longer to calculate every single frame. So it's actually safest to start baking your simulations, but we'll do that in a while. So right now you can actually see that if you take this box and move it around, the particles are no longer exiting the box no matter how fast we move the box, which is actually really cool, and I love this feature. The particles still are interacting with themselves quite a bit, but they can never exit this particular bounding box that we've created because we have all of those substeps initiated. And you can actually move this around in various ways, and you get all of these really cool animations of these spheres moving around, which is just amazing. So now that we have that, we can select our original cube, which is our geometry node object, and then actually finish off everything that's a part of the geometry node section. So the first thing is that if we actually switch off overlays and go to the rendered view and maybe remove our bounding box for now, we won't be able to see any of our particles, and that's because they're points and not actual objects. So we have to actually convert them to real objects before we render it. So to do that, we press Shift A and search for an instance on points node, and we actually instance an icosphere into it. Now these icospheres have to have radius equal to the radius of these points. So I can take this point radius and just plug that in to the radius of the icosphere. Next, I want them to be a little bit more subdivided, so I'm going to increase the subdivisions to 3 or even 4. Beyond that, I actually want the radius to be slightly smaller than the simulated radius so that at no point will there actually be real collisions between them. So I'm just going to go ahead and search for a math node and change this from add to multiply and multiply it by a value of 0.9 and plug that in just before the radius. Next, I want them to be shaded smooth, so I'll press Shift and search for a set shade smooth node, and I'll plug that in. After that, I can search for a set material node so that we can actually control the material. Now there's actually one last thing that I actually want to do in this animation, which is I want all the particles to have a different color when they're moving fast and a different color when they're moving slowly, or essentially 2 different materials. Now ideally you could use attributes and have like a nice range of colors so that as it moves the factor changes, but for some reason I tried that out, I've been testing it, and I haven't been able to successfully get it to work. When I figure that out, I will definitely create a tutorial on that, but till then I'm just going to use 2 different materials, one for particles that are moving really fast and one for particles that are not moving too fast. Then to actually select which material or which particle gets which material, I can press Shift A and search for another vector math node so that we can convert the velocity into just a singular value by using a length node. So this way we find out what the velocity is, or at least what the speed is, and then this speed, if it's greater than a certain value, I'm going to go ahead and set a different material for it. So I have to search for a compare node and plug this in. So let's say if it's greater than 0.5, then I want those objects only to get this second material. So I have to plug this output into the selection. Now, initially for all of the particles, whether they're fast or not, they should get the base material. So we select material from here. We'll go to the material properties and change this to slow particles. And if they're fast, we need a new material slot. So we press this plus button and then click new, and then change this name to fast particles. And then over here, we select fast particles. With that, the last thing that I wanted to do was increase the actual density of the point cloud. So I'm going to increase the density up to maybe 20, and then I'll go back to frame 0 and just play the animation, and that looks good. So the next thing is actually animating the outer sphere. So before we start the animation, we'll set all of our animation defaults. So we'll go to our output properties, change the frame rate to 30 frames per second, change the end frame to 150 so that it's a 5-second long animation, or in this case we'll do 300 and make it a 10-second long animation. Then the output folder can be wherever you want it to be. File format is going to be FFmpeg video, and encoding, I'm going to change the container to MPEG-4 with an output quality of perceptually lossless. Then while animating this outer sphere, it's going to be extremely laggy if I try to play everything together. So I'm actually going to select this cube, which is my actual particles. I'll actually change the name to geoparticles, and I want to actually disable it completely so that my system doesn't lag. So to disable it, I'm going to have to go to this filter button over here and add in disable in viewports as well. And then I'm just going to switch it off in the visibility, in the viewports, and in the renders initially while I actually do the animation of this sphere. Next, to actually do the animation, I'm going to increase the timeline a little bit, switch on overlays once again, select this cube, and I'm going to go down here and switch on auto keying. With auto keying switched on, whatever motion I make for this cube, it'll get stored in as keyframes down here. I also don't require any of these keyframes. I'll just select them and press X, delete keyframes. So with that, if I just press play and press G and move it around, the keyframes will get stored. So I'll press play and then G and then just move it around maybe like this, maybe give it some swirling motions like that, and then bring it back right to the center and leave it. Next, I want to actually go to frame 0 and then press I location and then press Shift D and bring that all the way to 300. After which, I'll just press A to select all of these nodes, then change from the timeline to the graph editor, and then I'll press Alt Shift O to actually sample keyframes, and then I'll press Alt O to actually smooth the keyframes out so that the motion isn't too jagged. Then if I actually play the animation, you should see how the motion is. We get quite some random motions here and there, which is exactly what I did, and that's good enough. Maybe I want these motions to be a little bit more exaggerated on the z-axis, so I'll just expand this object transforms, switch off everything except for the z location, and then with all of these selected, I'll just press SY and then just drag it up a bit, and that way we get some more exaggerated motion on the z-axis as well. So that seems good enough. Now we actually have to bake in the geoparticles simulation. So to do that, we can go ahead and unhide the geoparticles, and right now if you try to play it, it's going to be way too slow. So best practices is to first save it, and either way you cannot bake the animation without saving it. So press Ctrl S and save the animation. Once you have it saved, if you actually try to play the animation, you'll see that it's actually very slow and it's not able to calculate anything until you actually pause. So it's really hard for your system to take care of it. So the first thing that we'll do is change back to the timeline, and then with this geoparticles object selected, we'll go to the physics properties over here, and then there's a new simulation nodes section, expand it and click bake. Once you hit the bake, it's actually going to bake the simulation for every single frame, and you're just going to have to wait for the entire thing to finish. Once the baking is done, you should be able to play back the animation, and it might not go at real time due to the number of particles present in the animation, but the actual simulation and the positioning of these particles will be seen clearly. That way you can see whether you want some more motion to make the balls bounce around a little bit more inside, or if you're happy with whatever has been simulated. So right now I think for the most of it I'm happy with it, but I still want some more Z motion. So I'll go back to my graph editor with this original object selected. Again, only the Z location is present, so I'll just scale it on the Y, bring it up even more. And for these particles to actually respect the new changes that you just made, you're going to have to go to the physics properties again of the particles. So select it, and then you're going to have to delete the bake by pressing this button, and then you can press bake to rebake the new animation. So we'll just press bake again. So now I have the animation baked yet again, and now I like the motion of the particles even more because it's a little bit more exaggerated, so they move around even more and they show what exactly is happening with these particles. So that's good enough, and now we actually have to start off with creating the original materials for this particular object. So to create the materials, we're going to go ahead and change this graph editor back to the timeline, and we're going to bring it down. We're going to change the geometry node editor to the shader editor. Then we're going to change our viewport display to rendered, and we're going to switch off X-ray. After that, we're going to go ahead and set all of our animation defaults or our render defaults by going to our render properties, switching on ambient occlusion, bloom, and screen space reflections. Under screen space reflections, you're going to have to expand it and switch on refraction, because if you don't do that, you won't be able to see through this particular sphere. Next, the actual bounding box object is still not shaded smooth, so you can see the actual faces. I don't want that, so I'm going to click object, shade smooth. Next, we're going to start off with the bounding box material. So we're going to go to the materials, add in a new material, and we're going to call this as glass. And we're simply going to change the surface from principled BSDF to the glass BSDF. And down here for the settings, we're we're gonna have to go ahead and change the blend mode from opaque to alpha hashed or alpha blend, and we're gonna have to switch on screen space refractions by checking this button. And I'm also gonna switch off shadow mode, so I'm gonna have to change it from opaque to none. Next, although this is realistic glass, or at least realistically calculated glass, which doesn't look realistic at all, we want it to actually be more stylistic, which means we want to be able to see through it a little bit more. So to do that, we're just gonna go ahead and decrease the roughness from 0.5 down to 0.2, and I'm going to change this IOR from 1.4 down to 1.1, and that way we'll be able to see more of these spheres. And I'm also going to just increase the color by a tiny little bit. Next, we'll go to the world background, so we'll go here and we'll just increase the color all the way to white, and then we can start off with the actual spheres. So we'll select our geoparticles, and the first material that's selected is fast particles. So the fast particles, I want them to actually be emissive, so I'm going to take the principal BSDF and press X to delete it. Then I'll press Shift A and search for an emission node, and then I'll just plug that into the surface. And for the color, I'll just give it this bluish color, and I'll increase the strength to something like 20. Now, if we actually go to some frame where there's quite a bit of motion, we should be able to see these emissive particles. But to help see them better, the first thing that I don't want is this light. So I'll just go ahead and hide it for the time being, and then I'll just let the animation play, and I don't see any of them lighting up. So since they're not lighting up, we're gonna have to go back to my geometry nodes object, switch back to the geometry node editor, and start playing around with this greater than threshold. So let's first reduce it down to 0 and just check what the situation is, and we see that none of them are getting those fast particle objects, which means that we missed something out. And yes, right now it's a single instance. You can't set separate materials for different instances. We need every instance to actually be realized, and then we can separate out materials for each of them individually. Hence, after the set shade smooth, I'll press Shift A and search for a realize instance node, and before plugging that in, just make sure that you press Ctrl S to save your project. Then I'll take this realize instances node and just plug that in before this first set material. Now all of them are lit up because we have anything that has a velocity greater than 0 is going to get that fast material. So I'll increase this back to 0.5, and way too many are still switched on, so I'll increase it to 1, and I'll keep increasing it and playing around with the values till I get a very small number, or a number that I'm happy with, to be lit. So for now, I'm going to go with the value of 1.5, and that should be all right. Next, I can go back and increase my world background all the way to white, and I can switch back to the shader editor. Now we are done with the fast particles. Next, I want to play around with the slow particles, so I'll go to my materials, select slow particles, and for these I just want them to be fairly metallic with a fairly low roughness, so maybe a roughness of 0.4. Along with that, I'm just going to decrease the base color a little bit so that they're much darker spheres. Next, it's best to actually work with a background plane, so I'll press Shift A and search for a mesh plane, and I'll just scale it up. So for now, I'll scale it up by another 20, and then I'll just press GZ and bring it down. Then I'll change my camera to look at it from a slightly higher angle, select the plane, and then add in a new material for it, and I'll just play around with the base color and things like that till I get something that I'm happy with. Of course, this might change before I actually hit the final render, so I'm not going to waste too much time on this. It's going to be very similar to backgrounds that I've done in other videos, such as this particular video that you should definitely check out. I'll have it linked in the top right corner if you haven't seen it already. So that's the material that I'm going to be creating, and with that, all you have to do is press render animation, but you have to select a nice camera position as well. Don't forget that. Press Ctrl Alt Numpad 0 to snap camera to view. Select the camera and then press N to go into the side panel. Change it to view and then click lock camera to view, and then you can navigate around exactly how you want, and just make sure that you get a position that you're happy with, because the particle is going to be moving quite a bit. We've added in quite a lot of motion, so it's actually a good idea to hide your geoparticles object and just play the animation to see whether or not your sphere is actually going outside the camera view. So let's just uncheck camera to view, and under my camera properties, go to viewport display and increase passport out all the way to 1. And you see there are a few things that I want to change. Firstly, the background isn't even straight, so I'll go to the camera properties here and just change this Y rotation to 0, and that should make the background completely straight. And then you can just see how this particle is moving around. I also don't want any of these camera keyframes to be created, and that got created because of this auto key. So make sure that you switch off auto keys and then press AX delete keyframes and then change this back to 0. And yeah, right now the sphere is going out of my view. So make sure that you increase your clip end as well if necessary. I'm going to increase that all the way to like 1000. And once you're happy with the positioning of the camera, all that's left to to do is make sure everything that you want to be unchecked is unchecked, and then press render animation. Hopefully this one helped demystify simulation nodes a little bit more. Remember, practice makes perfect, so creating more simulations and implementing different ideas that you might get in your head will definitely help improve your proficiency with simulation nodes. Both of these effects, the one that we did today and yesterday, were fairly similar and had a very similar setup, but we added in a lot more features in this iteration today. In the coming few days, we'll be doing completely different types of simulations as well. So if you enjoyed this video, be sure to subscribe and stay tuned for future videos as well. Until they come out, I have a lot of content present on my channel, and I'm sure you'll find a lot of it helpful to either learn certain tips and tricks or just get motivation to create some animations of your own. So until the next video comes out tomorrow, keep creating and stay creative.